In our previous lesson, we evaluated limits both graphically and numerically. Graphically, you basically look at the graph, and as x approaches some number, if the graph comes together at that x coordinate, the limit is that y value. If the ends of the graph do not come together, then the limit does not exist. Numerically, we made a table, and from that table, we saw if both sides from the left and the right approach the same number. If they do, the limit is that number. If they don't, the limit does not exist. Today we're going to look at evaluating limits analytically, which basically means by plugging in directly or by doing some algebra. We might have to do some algebra to simplify the expression a little bit. So first we have some basic limits by direct substitution. And intuitively, I think these are pretty self-explanatory. The first one is the limit as x approaches c of b, where b is just some constant. So it's saying if I have a constant function, like y equals 5, the limit as x approaches some number c is going to be, well, the same as that constant function, let's say 5, because the graph comes together from both the left and the right. So down below, the limit as x approaches 3 of 4 is just going to be 4. The second one, the limit as x approaches c of x of some linear function is c. So what they're saying here is basically, if I have a linear function, let's just say a simple one, y equals x, the limit as x approaches some number c is going to be, in this case, that number c, because the function is y equals x, so x would be the same as y. Down below, it's not just the limit as x approaches negative 2. I don't know why that's over there. It should be over here a little bit. Of x plus 3. X plus 3 is still a linear function, so I can just go ahead and plug in negative 2 for my x, and negative 2 plus 3 is 1. So the limit as x approaches negative 2 of x plus 3 is 1. Third one, the limit as x approaches c of, oops, I have a little typo here. This should be x to the n power equals c to the n power. Again, for exponential functions, you could just do direct substitution, which means for my first example, or third, the limit as x approaches 5 of x squared is simply 5 squared, which is 25. So nice and easy, basic direct substitution. Now we've got some properties of limits. And again, I think these are all pretty intuitive, but let's see what you guys think. Scalar multiple. If I have the limit as x approaches c of b of f, b times f of x, this is equal to b times L, where up here they tell us that the limit as x approaches c of f of x is L. So basically what you can do is just find the limit as x approaches c of f of x and multiply it by that constant out in front. I think that it'll become a little more clear with some examples what I'm talking about here. Number 2, the sum or difference. So the limit of the sum or difference of two functions is the same as the limit of the sum and difference of their limits. Product, same thing. The limit of a product of two functions is the same as the product of their limits. Number 4, the limit of the quotient is the quotient of the limits. And let's see, number 5, the limit as x approaches c of f of x to the n power is that same limit raised to the n power. So basically it's just saying that the limit of some combination of two of these functions is the same as the limit of the two. So actually I'm going to skip down in the notes a little bit. I'm going to skip ahead just because I think it'll be, well, no, we'll stay here. Okay, so for number 4, the limit as x approaches 1 of 3x squared minus 1. So I'm going to do this once. I never really want you guys to do this. I'm just kind of showing you what the properties mean. This is the difference of two functions. I have the function 3x squared and 1. So I'm going to be using actually the sum and difference property as well as the power property. So they're basically saying that you could split this up into the limit as x approaches 1 of 3x squared minus the limit as x approaches 1 of 1. Now, using my properties, for example, in the first one, the scalar property, where if I multiply a function times a constant, here I'm multiplying the function x squared by 3. This is the same as 3 times the limit as x approaches 1 of x squared minus the limit as x approaches 1 of 1. Now I can evaluate, this is 3 times, I'm going to plug the 1 in for x squared, so I get 1 squared. And the limit as x approaches 1, we saw this in the very first property of a constant, is 1. And 3 times 1 squared minus 1 is simply 2. Now, you don't have to use those properties to actually do the problem. You can just do it by direct substitution. That's how I'd like you to do it. Just go ahead right at the start and take 1 and plug it into this expression. 3 times 1 squared minus 1 is 2. The reason we have these properties is twofold. It's going to make some more complicated functions later on easier to evaluate. And also for the AP test. The AP likes to ask you some crazy questions sometimes to test your knowledge of these properties. Here, I'm going to scroll down a little bit and look at number 14 real quick. So there's a lot of information here. Given that the limit as x approaches, I'm not going to highlight that, as x approaches 4 of f of x is 16, the limit as x approaches 4 of g of x is negative 2, and then limit as x approaches negative 2 of f of x equals f of negative 2, which is 7. And they're saying for some reason f is continuous at 7. We're going to talk about continuity later. The limit as x approaches negative 2 of g of x is 0, limit as x approaches 16 of f of x, and limit as x approaches. So I have the limit for a bunch of different values. What is it? Negative 2, 4, and 16. So the first one, the limit as x approaches 4 of f of x times g of x. The product property says that that's the same as the limit as x approaches. So 16 times negative 2. So my answer to this problem is simply 16 times negative 2, which is negative 32. For part B, the limit as x approaches negative 2. So now I'm focusing on this one and this one. So I can write this as the quotient. The limit as x approaches negative 2 of f of x is 7 over g of x, which is 0. So 7 divided by 0 does not exist. This is not the indeterminate form because it's not 0 divided by 0. It does not exist. Okay, moving on. The limit as x approaches 4. So I have f of x, which is 16, minus g of x, which is negative 2. So it's 16 minus a negative 2, 18. The square root of f of x, this is the power property. So as x approaches 4, so I'm using this, so this would simply be the square root of 16, which is 4. Let's see. Part E, as x approaches 16 of f of x, so that's this one. So that would be the square root of 5 to the 4th power. However you want to do this, it's 5 to the 1/2 to the 4th. The power times the power, you multiply. It's 5 squared, 25. And here in part F, I have both a sum and the scalar property. Again, this is simpler than it might seem at first. This is just 0.5, and the limit as x approaches 4 of f of x was, what is that, 16? Plus 4 times the limit as x approaches 4 of g of x, negative 2. So So half of 16 is 8, negative 8, so 0. Okay, so that's how AP is going to test you. They might use, they might give you values for limits like this. They can do it in a table. They can do it in a combination of a graph and a table, a bunch of different things. But that's how they're going to look at it. Going back. So all these problems are basically, not basically, they are direct substitution. So I have the fifth root of 32, which is 2. Let's see, the limit as x approaches pi. So I have the product of x, the function x, times cosine of x. So this is going to be pi times the cosine of pi. Now pi is just pi, cosine of pi. I don't know how you guys do this. Sometimes I like to think about the graph. Cosine looks like this. So at pi, the function would have a value of negative 1. So it's a negative pi. And last but not least for this part, the limit as x approaches 2 of that rational expression. I can take 2 and plug it into this expression because it will not give me a denominator of 0. It'll give me, what is this, 4 plus 8 plus 3 over 1. Oop. Knocked myself out there. Oh boy. Give me a headache. Oh, and it's all gone. So I believe what I had here, let me go back, is 2 squared plus 4 times 2 plus 3 over 2 minus 1. 4 plus 8 plus 3 over 1, 12, 15. Okay, I'm going to go back and redo those other 2 problems later. I don't know what happened to them. I believe this was, well, I'll just do them now. The fifth root of 32, which is 2. And here I have pi times cosine of pi, which is pi times negative 1, so it's negative pi. You definitely have to have your values of your trig functions down pat. It's going to save you a lot of time in this class, so if you don't know them, you might want to go back over the unit circle. All right, here's the big part for this lesson. Functions that agree at all but one point. If we take a look here, this rational expression, x squared plus 4x minus 6 over x plus 6. If I take the limit as x approaches negative 6, I'm going to get negative 6 squared plus 4 times negative 6 minus 12 over, now I see a problem right here, negative 6 plus 6. So what I'm going to get is 36 minus 24 minus 12, which is, over 0, which is 0 over 0. This is called the indeterminate form. It does not mean that the limit does not exist or that it's 0. It means that there's something else going on here. There might be a limit. We have to do a little bit more work to figure it out. So we just have to go back into our bag of tricks from algebra and try to simplify this expression somehow. So I'm going to erase this, and hopefully you're thinking, since it's a rational function with polynomials, you're going to factor. So I'm going to take the limit as x approaches negative 6. I'm going to factor my numerator. Let's see, x and x. Factors of 12 that give me 4 are 2 and 6. And I need the 6 to be positive and the 2 to be negative. They're different signs because the 12 is negative and the 6 is positive because the sum of negative 2 and 6, I want it to be the positive 4. Now, if you'll notice, I have an x plus 6 on the bottom. I can cancel out the 2 x plus 6's. What this allows me to do is evaluate a similar expression, just the limit as x approaches negative 6 of x minus 2. Now, since this is linear, I can go ahead and Simply take negative 6 and plug it in for x. Negative 6 minus 2 is negative 8. So just what's going on here basically is the graph of x squared plus 4x minus 12 over x plus 6 is the same as the graph of x minus 2, except it has a hole, if you recall, at x equals a negative 6. So just a kind of generic graph there. It's the same as the graph of x minus 2, but down here I would have a hole when x equals negative 6. But we know from evaluating limits graphically, if I go from the left and from the right, my graph or my fingers come together. So that's why I have the limit as negative 8. All right, just a little more practice with factoring. So let's see, let me switch colors here because I'm going to run into something else. I have the limit. So first of all, I should test out by direct substitution that I do get the indeterminate form. I'm going to save you a little bit of time here. If you do plug negative 4 into the numerator and denominator, you will indeed get 0 over 0. That's why I picked this problem as well as number 10. I think in number 10 you could just see that it's going to be 0 over 0. So it is the indeterminate form, so you have to try a little something. So I'm going to factor again. So I have the limit as x approaches negative 4 of, let's see, okay, so I have 4 terms up here, so I'm going to factor by grouping. The first 2 terms I'm going to take out an x squared, and the next 2 terms I'm going to take out a negative 1. And I get the same binomial in the parentheses, so I know that's good. On the bottom, x plus 1, x plus 4. So I have the limit as x approaches negative 4 of x plus 4 times x squared minus 1 over x plus 1 times x plus 4. Again, my x plus 4's cancel out, and I can actually factor the x squared minus 1 a little more to reduce with the x plus 1 on the bottom, but I don't have to because it's the limit as x approaches negative 4, so I can go ahead and just do direct substitution with this expression. So what do I have here? I'm going to plug in negative 4. What is that? 16 minus 1 over negative 3. And I get negative 5. So, moving on, last example. I should have enough room here. Again, I can see that I'm going to have 1 cubed minus 1, which is 0, over 1 minus 1, which is 0, which is indeterminate. So, I'm going to take the limit as x approaches 1 of, let's see, the difference of 2 cubes. So how I remember it is small parentheses, big parentheses. Let's see, it's x cubed and 1 cubed, so it's an x and a 1. It's x squared and 1 squared, which is 1. And the product of the two, 1 times x is x. The sign on the difference of 2 cubes is found by the acronym SOAP. Same, opposite, always positive. My sign is a minus, so same, opposite, always positive. And yay, my x minus 1's cancel. So now I can evaluate the limit as x approaches 1 of just x squared plus x plus 1, which is 1 squared plus 1 plus 1, 3. So, if you do direct substitution and your numerator and denominator are both 0, you have to try something else. That something else is, our first trick is just factoring and canceling if it's a rational expression. Let's see, it looks like number 3 is going to be the same way. I have the limit as x approaches 3. Now I'm going to factor my denominator as the difference of two squares, and hopefully you recognize that the numerator is written a little backwards. So what we can do is we can, trick is factor out a -1, and that would change the x to a positive and the 3 to a negative. Now I can cancel out the x minus 3's, and now I can do direct substitution, because I simply have the limit as x approaches 3 of -1 over x plus 3, -1 over 3 plus 3, -1/6. All right, two more. Number 12 has, well, I can't factor that. Oh, but what I can do is I can rationalize the numerator, a trick from Algebra 2 as well as pre-algebra. So I'm going to zoom in a little bit here. I'm going to multiply my numerator and denominator by the conjugate, which is the square root of x plus 1 plus 1. Same terms, different sign. On the bottom, it's the square root of x plus 1 plus 1. I'm multiplying it by 1, so I don't change its value, only its form. What I have here is the limit as x approaches 0 of. Now, when you multiply by conjugates, the trick is it's the first expression, or the first term, squared minus the second term, squared. And on the bottom, well, don't multiply out the x yet. I'll show you why you actually just don't have to. Makes your life a little easier. And I can go ahead and clean this up a little bit. I have the limit as x approaches 0 of x plus 1, the square root of x plus 1 squared is x plus 1 minus 1 over x times the square root of x plus 1 plus 1. Now here a lot of stuff happens. My x's cancel out. Oops, that x and that x. And 1 minus 1 is 0. So I still have the x up there, so I'm holding its spot with 1 over, what do I have here? The square root of x plus 1 plus 1. Now it's a little bit of work, but what I can see is I can plug in the 0 for my expression right now, and I won't get 0 over 0. I will get 0 plus 1 plus 1, which is 1 over 1 plus 1, which is 1/2. All right, one more problem. If you get some trig expressions, it might be helpful to, well, first, if I do direct substitution, I will get the tangent of 0, over the sine of 0, which is 0 over 0, which is indeterminate. So I have to try some tricks. Here I'm not going to factor, but I'm actually going to rewrite my expressions. I'm going to rewrite this as maybe tangent of theta times 1 over sine of theta, and then I can make this sine of theta over cosine of theta using an identity. And we see my sines cancel out. So what I'm left with is the limit as theta approaches 0 of 1 over cosine of 0. I'm going to try direct substitution. Let's see, cosine of 0. Oh, I can do that. Cosine of 0 is 1, so this is 1 over 1, which is just 1. All right, a lot of work there. We're going to practice on these for a couple days. Talked about this, and we will do the squeeze theorem actually in the next lesson. Thank you.